that's okay. We'll have volume shortly. So, my only disclaimer is go blue, obviously, right? So, my name is Mark Salamango. I'm the Chief Information Officer for the Michigan Center for Integrative Research in Critical Care, or MCIRCC for short. We're a part of emergency medicine at the University of Michigan. And the way I see it, one of two camps come to a talk like this that's entitled Data, Data Everywhere, Nor Any Drop to Drink. There's one camp who's been looking through the schedule and going boring, 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 boring. Hey, that sounds interesting. This guy's ripping off 19th century poet Samuel Taylor Coleridge. And you got the other camp that was like, yeah, obviously, this is something that we need. So we're going to break this talk down into a couple sections. I'm going to start off by asking a question, and then there will be some jokes. And the only reason I point that out is because the worst thing in the world is when you're up here and you think you got a good joke and no one laughs, so I'm encouraging you to laugh. Hopefully you know where the joke is. And then we're going to talk about how we're using data and the architecture that we've set up to collect data and then use it. And then finally, we'll just go over real quickly how you can save at least one life in this room. I'm sure many more. Okay, so the question, has anyone ever been super close to something, but they just can't grasp it? I mean, they're right on the edge, they can almost taste it, but they can't grasp it. So I'm a visual guy, so I like to use a lot of pictures in my talks. And so I'm going to give you an example of that. Right? It's so close, but you can't touch it, right? Not yet, not until his master says it's okay. Now, honestly, I had several other pictures that I wanted to use, but I couldn't get the photographer to give me credit or give me the ability to use it, permission. And so I had to improvise a little bit. So, yeah, so close, right? Just could almost taste it. Another example, my tongue stops right about there. It's just so close. This one, I think we've all had this one, right? It was just so close, and they were cleaning the restroom. It was almost a disaster, right? And finally, sometimes being 6'5" has its downside. So that was the last joke. Sorry, they weren't that great. But you do not have permission to laugh throughout the rest of the talk, okay? All right, so what is this really about? This is about, the title from the talk came from The Rime of the Ancient Mariner. It's a famous poem. And at one point in the poem, the captain finds himself in the middle of the ocean, no water on board the ship, and he's looking around and he's saying, like, water, water everywhere, nor a drop to drink, right? Because they can't drink it because it's salt water, obviously, right? So while we're not talking about water here, when you enter an ICU, you have a similar thing with data, right? There's data everywhere, but how much of it really are we capturing? In fact, we know, medications, they get scanned in most places. You have things like ECG popping up on a screen, but how many people are really saving those waveforms? How many people are really saving the waveforms for pulse oximetry, or are saving the waveforms for intracranial pressure and things like that? It turns out there's a lot of rich information in those waveforms. In fact, these are the kinds of things that data scientists drool over, right? Any data scientists in the room? There's at least one, okay? I know there's two because he's over here. So the point is, if you're not collecting this stuff, we may be missing some things, right? Now, I know that we're collecting some pieces in an EHR, but the kind of data I'm talking about here is legitimate physiological waveforms. Now, if you take an ECG, for example, you may have 12 leads, and those leads could be spitting out data at 240 hertz up to 500 hertz. So that means every second you're getting 240 data points for each one of those leads. So I see why people don't do it, because it's hard, right? There's a lot of data, it adds up really quickly. But the important thing here is that there is so much richness in that data that if you have the right data scientists who know how to do signal processing, you have the right tools, you can create some amazing things. So this is truly big data, right? Okay. I thought I told you there was no more laughing. Okay. So what I want to do is I want to set up a demo. And I explain to you why we do the things that we're doing at the University of Michigan, why we're storing all these physiological waveforms, why we're storing numeric data, demographic data, medications, labs, all that kind of stuff. In this demo I'm going to show you is a project we're working on called AHI, and it's the Analytic for Hemodynamic Instability. And so what we've done here is, again, we store this data, and then we present it in a way that our researchers can use it to build predictive models. Okay, now there are a lot of steps in making this happen. So first we're storing this data. We have to time align it because remember that last slide, we're getting it from a lot of different places. And if it shows that you gave norepinephrine at 1 o'clock and it was really given, and you're seeing a waveform and the waveform is not aligned with that, then you can end up with some goofy machine learning models. So once we have all this data stored, we build cohorts, right? We're looking for a group of people that had a particular event happen to them or something went on while they were at their stay. We build that cohort, then we pass that on to clinicians who can then annotate that cohort, and we have tools that do that. And then from there, we pass it to our data scientists, and our data scientists can make these predictive models. Okay, so I'm gonna show you a demo. Everyone cool with that? Sorry, I'm moving my head, and it's getting loud and it's getting soft. All right, so this is Ahi in action. Let me talk through the interface a little bit here. So again, this is a real patient who had a GI bleed in our ICU. And what we have at the top here is a gauge that's predicting how the patient is going to do in the future, right? So a couple hours in advance, something could happen or maybe not. If it's in the green, we're saying, hey, this patient looks like he's on the trajectory of getting better. This bar right here is showing us that according to our model, his vitals and everything that's coming into it right now, the whole waveform is saying that, you know what, everything is okay. Okay, now the other thing to notice here is I have about 18 hours worth of data, and I know this is a 20-minute talk, so I'm gonna just have to have you guys all wait here until we get to the end, just so you can see the, oh, okay. So anyway, each one of these little clicks that you see going by is 3 minutes of time. Okay, so I'm gonna fast forward a little bit into this patient's stay. And at this point, you're starting to see our prediction. So maybe we're 10 hours in, 8, 9, 10 hours in, and you're seeing that we're starting to make a prediction that their trajectory is down. Some bad things are going to happen. They're going to become hemodynamically unstable at some point in the future. And you can see it's again going down, but right now the model is saying everything looks fine. In fact, the vitals for this particular patient looked fine, right? So normal blood pressure, everything was normal. No fever, he was doing well. But again, over time, we're starting to see this go down. Now, you saw we jumped into a little yellow section here, and what'll happen is he becomes mildly hypotensive, but then he bounces back because the human body is able to compensate. And then it goes down again, and I'm gonna fast forward a little bit more. And at this point, we've been predicting this for several hours, and intervention was given. This patient crashed, right? So they had to do some life-saving maneuvers to get this guy back, okay? So this is Ahi. This is the reason we store all this data, because we're able to take these physiological waveforms, put it into a predictive learning model, machine learning model, and we're able to make these predictions. And this is just kind of the tip of the iceberg. All right, so we're gonna go back to the tap dance in front. Okay, so how is it possible that we can do that? Again, lots of data coming from lots of different sources, right? It's not just the ICU, we're pulling data from all these different databases, either internal to U of M or external to U of M. So the way I'm going to describe this is I'll give you a little bit of a high-level view, and then I'll drill a little bit into the details and show you how this is all put together. So when I think about our architecture, I like to think about it in real time and then research. So the real-time portion is the portion that's taking data off monitors, it's making that prediction, and it's giving it to the clinicians. The research portion is, hey, we need to save this stuff so that our data scientists can make use of it later. Okay, now on the real-time side, it's very simple in this diagram. In practice, it's a little bit more difficult. We start off with our patient monitors. We're a GE shop. Those monitors talk to a gateway. The gateway aggregates data from all these different leads and things like that, and then it passes it into a streaming engine. And I'll explain the streaming engine in a second. At the same time, Epic, our EHR, is getting data pulled from it into this streaming engine as well. And then we output a score, or the trending trajectory of the patient, into a partner of ours called Airstrip. And Airstrip allows us to visualize all this stuff on mobile devices. Okay? So peeling back the onion on the streaming engine, what we're using this for is a couple different things. So there are a couple different streaming engines you can get to do this kind of thing. We're using something by IBM called InfoSphere Streams. There are some open source technologies that do similar things as well. And they all use things called operators or something similar. And so what we do is we string together these operators, and this one will do something maybe like ridding the world of baseline drift, right? When your signals are kind of creeping up or down. They'll do some filtering, maybe some other things. And at the end of this chain is our model. So we've taken this data, because it can get a little ugly, right? If you've seen ECG data, someone moves, you get artifacts and things like that. So we got to clean that up first. Once we've cleaned it up, we pump it into our model, and then we get a score. The score comes out, gets presented to the clinician, and then they can decide or not to decide to take further action. On the research side, it's very similar. So we take our patient monitors, they talk to a gateway. The gateway deals with pulling the data into packets that we care about, and then it passes it on to a streaming engine. The only difference here is that the streaming engine is also doing de-identification in real time as well, so that we can land it into a platform that we call SIRCC. Now, when I was talking a little bit earlier about how we have to time align data and we have to do all these different things to clean it and stuff like that, that's what SIRCC is doing. And so we built an abstraction layer on top of all the different repositories that we talk to, so that it would be easy for our researchers to make use of this data. And again, we're able to pull in sources like mimic data, things like that, into our research repository called SIRCC. So this is the ugliness when you put it all together. And I'll just walk through it really quickly, just to give you a little bit more of an idea of how this works in context. So again, we have our real time, we have our research over here, and then I have another section that I'll describe shortly. So again, we have our monitors that are spitting out data into a gateway. The gateway is going into our de-identify piece of our streaming engine. This is our streaming engine that deals with all our analytics. We pop out a score. The score gets delivered to mobile devices. So this is basically how it's working on the real-time side. Now the other thing that we're doing at U of M is we're building lots of wearable sensors. And so there are several talks after this session in SunD that you should check out, where you're going to hear more about our analytics. You're going to hear about some of the mobile sensors that we have and we've developed as well. So we have a piezo ring. We have something called Drive that uses bioimpedance to measure fluid volume. We have some wearable ECG patches, and we're doing some Raman spectroscopy. All that stuff talks to a sensor server, which does the same thing as this gateway, turns these bits of data into packets that are readable by the rest of our system. Now, that's the real-time side. What we're doing as well is we're storing all of that data into this SIRCC platform so that our researchers can make use of it, right? And none of this would be useful if we didn't make this easy for researchers to use. I mean, some of our scientists, clinicians, I mean, they're really bright people, but I want them to focus on the saving lives part and not have to worry about how to write SQL queries or how to write Java code or how to time align variables and things like that. So what we've done is we've created a whole suite of tools that allow them to create cohorts. If a clinician's interested in people that have had hypotensive episodes, there's a web app, you go into it, you look for people that meet the criteria, and it builds a virtual cohort for you that you pass on to all the other applications that we have. We have an application we call Tater. It's our annotation software. We couldn't annotate these waveforms any other way. If we had to do it by hand, it would take forever. So we built this web app that allows them to take these waveforms, look at their complete state, and then highlight areas of interest. We have several others that we can talk about later. So as we were building this thing, one of the things that we noticed is there are gaps all over the place, right? You can buy hardware all day, you can buy software all day, but where the rubber meets the road is making it so that some data can come in from a sensor and it can get placed in an area in a way that people can actually use it. And so we bought this. So we bought a Hadoop distribution from IBM. We bought something called a Pure Data for Analytics appliance. And then we bought a streaming engine and some presentation layer software from Airstrip as our partner. All the rest of this stuff is stuff that we've had to build on our own. So what you'll often hear is, oh, just buy this big data solution or buy this big data solution. Well, I'm here to tell you, big data is not like a TV dinner. You don't just buy it, rip off the foil, put it in the microwave, cook it, and you're done. It's really much more like creating a culinary meal, right? Where you gotta find the stuff, find the ingredients, you gotta cleanse them, you gotta prepare them, and along the way, you're probably gonna cut yourself. And then you gotta mix it together so that someone can make use of it. So, the last thing, and I really want to appeal, data scientists around the world want to appeal to you. There's a lot of rich information out there that we can make use of. These waveforms are important. There's a lot of little nuggets in there that we can make use of. And my fear is that if we don't start doing that kind of thing, we're going to end up seeing a lot of this on the streets. And we don't really want that, at least for this guy over here. All right, so that's it. If you have any questions, I'd be happy to take them if we have time. Otherwise, you can meet with me afterwards.